All right, it is 10:20. Why don't we go ahead and begin? So, yeah, administratively, tomorrow you have a quiz. The quiz covers 15.1, 15.2, 15.3, and 15.10. That is through the Monday content there. Um, Today, I'm hoping, so 15.4 stuff is dealing with polar transformations. So 15.10 was kind of dealing with arbitrary transformations. And as you know, we need to have this absolute value of a Jacobian when we make such a transformation. And here, as you saw in the pre-class video, right, when we switch into polar, this is always just R. And so that's quite nice. I guess any questions before we jump into the pre-class video for today? All right. Well then, why don't we go ahead? And so polar, we've already seen these transformation equations. They're on our formula sheet. We've also seen them in calculus 2, most likely. So this is the classic r squared equals x squared plus y squared, and then x is r cosine theta, y is r sine theta. These are also the same as cylindrical, right? When we convert into cylindrical for 3 variable transformations. As we saw here, right, I told you just to believe me that you need this extra r. Of course, because we talked about 15.10, right, we already know that this is going to be because of the Jacobian. There's also a geometric way that you can come about this. And so this is okay, and you can do this in kind of 2 variables in a 2-dimension situation, and it's fairly reasonable. However, when you jump into 3 variables, and you have these volumes, right? Instead of dA, you'll have dV. It becomes a lot harder to visualize. And so that's really where the Jacobian will shine. So all of these, again, can be calculated via a Jacobian, or you can give some geometric argument about why you need this extra R thing, right? So when you switch, when you apply some transformation, you always need to include this absolute value of your Jacobian. In our case, right, when we switch into polar, we need the R. All right, so that's the main things for the pre-class video. Any questions before we jump into the new stuff for today? All right, then, let's do it. So, switching gears here, let's put our nice new result in a box. So if you would like to evaluate out a double integral, one option that we now have is switching this into our polar coordinate system. If you swap it into polar coordinates, again, don't forget to include in this Jacobian our R when we switch into, sometimes I refer to this as an integration factor, right? When you switch into polar, you need to include this integration factor, which of course comes from the Jacobian. If you would like to calculate out area in polar, all right, well, you would have 1 times r, dr d theta, or of course, 1 times r is just r. So if you prefer to just write r there, that's also perfectly fine. With that, we have really all of the new content, the new theorems, and everything that we need in order to do all of our problems. So the rest of the class is really just spent getting some examples under our belts to kind of showcase how do we actually use these things in practice. So maybe starting off here, I would like to convert my double integral here into a polar integral and evaluate. So the first thing is, and again, in the mindset of trying to maximize partial credit, you know, if this was to show up as a standard response style question on a quiz or an exam, I think the easiest thing to convert into polar is always the function itself, right? What are we actually integrating? In this case, we have x plus 2y. We need to come up with a polar equivalent to that. Well, luckily on our formula sheet, we know that x is the same thing as r cosine theta. So that would be a way to represent x in terms of r's and thetas. We know that y is the same thing as r sine of theta. And we can transform, instead of dy dx, I'll do dr d theta, and then, well, don't forget this extra r, right? So anytime that you convert into polar. We need this r. All right, so I think that's all of the low-hanging fruit right here. Next, we need to think about our bounds, right? And we need to rewrite our bounds instead of in terms of x's and y's and whatnot. We need to write them in terms of r's and thetas. So similarly to 15.3, right, the only surefire way that I know to do this is to sketch a picture. And so we're going to go ahead and sketch a picture of our bounds. So our bounds here are y equals x and y equals the square root of 2 minus x squared. And then we shade between x equals 0 and x equals 1. So again, kind of, I just wanted to emphasize, right, our inner bounds are y bounds, our outer bounds are x bounds. So you can put x equals and y equals for those, if that helps you. All right. So if I was to sketch a picture of this, y equals x, I'm pretty confident in, right? So y equals x just looks like, well, slope 1, intercept 0. Next up, y equals the square root of 2 minus x squared is a little bit more confusing. However, I think we've seen some problems recently that maybe should remind us that a good thing that we can do here is to go ahead, square both sides, and rearrange. And now we can see that this is actually part of a circle, right? So x squared plus y squared equals r squared is the classic equation for a circle. So really this is a circle of radius root 2. So a radius root 2 circle centered at the origin. Because it's y equals the positive square root, right? We're only going to have half of our circle. So it's going to be where our y values are positive. Remember, if we were working backwards to get to this, normally when you take the square root, right, if I was working backwards in order to get this, I would need to include the plus and the minus. And that would correspond to the top half of the circle and the bottom half of the circle, where the y's are positive and where the y's are negative. However, in our problem, right, it was given to us that this is only the positive square root. So, okay, that means that we're really interested in the top half of our circle. So something like this. And so this is a circle of radius root 2, I suppose. So I'll put a little root 2 here to remind me. And then I need to shade between x equals 0 and x equals 1. And I can see that there's kind of a couple of regions that are touching these curves that I've drawn here. So maybe I need to reemphasize that as I'm traveling in my y direction here, so thinking about traveling in my y direction, I need to enter in through y equals x, right? That's my lower bound of integration here. So if I'm traveling up, I need to enter in through y equals x, and I need to exit through my circle, my positive square root of 2 minus x squared. So I'm going to exit through my circle. And again, I'm only shading between x equals 0 and x equals 1. So with all of that information, I'm thinking that maybe this is the right thing to be shading. At least here, right, I see that x equals 0 is certainly the left-hand side of this region. I'm hopeful, although it still requires me to double check, that maybe this is x equals 1. That would be quite nice. And then as I'm traveling in this y direction, I would enter in through this line, and I would exit through this top half of the circle, right? As I'm traveling in the y direction, that's how I would enter and exit. So I just need to double check that, right? I should shade to this point of intersection, that hopefully this is x equals 1. And so in order to check that, well, this is where the curves y equals x intersects with the top half of the circle, right? So that was this positive square root of 2 minus x squared. So if I want to check where do these things intersect, right? Well, I can set them equal to each other like we did in our old algebra days. So this would be x is equal to the square root of 2 minus x squared. I could square both sides. I could rearrange, and I could solve for x. So this will give me that these actually intersect in two places, x equals positive 1 and x equals negative 1. So this x equals negative 1 actually is corresponding to the bottom half of the circle. The bottom half of the circle intersects with the line over here. That's where x is negative 1. But we can see that we're clearly in the first quadrant. we're looking for the intersection in the first quadrant, and that should have a positive x value. And so yeah, x equals +1 is indeed where these two things intersect. So now I'm quite happy about the picture that I've drawn for my region of integration. The final step that I need to do is, of course, convert this into r's and thetas. So we know that y's, right, when we travel in our y direction, we go from down to up, right, from the smaller y's to the bigger y's. If I'm traveling in my x direction, imagine if I'm integrating with respect to x first, we travel from left to right. We think about how do we enter and how do we exit our region. So maybe the good first thing that I should think about is, how do I travel when I'm traveling in my r direction? Small r's, right, first of all, in our class, we're not allowing for negative r's. So small r's are always at the origin. That's when r would be equal to 0. And these radiuses, as they get bigger, right, they come out of the origin. So stuff like this. Now, of course, that there are lots of these rays, these r's coming out of the origin that don't intersect our region whatsoever. And likewise, when I'm drawing my y's, right, these arrows that go up, I don't often draw arrows like way off to the left or way off to the right. I'm really interested in the ones that actually intersect our region. How do we enter and how do we exit? Of course, some of them never enter or exit, right? They just miss it completely. And so for those ones, I'm not really so interested in these. And likewise with the r's, right? I'm not going to kind of draw a lot of these that don't intersect. But for the ones that do intersect our region, we have to think, how do these enter and how do these exit our region of integration? Well, to me, it looks like as soon as I take the tiniest step off of the origin, I am in my region of integration. I have entered. So what would you propose should be our lower limit of integration? R equals what? 0, right? Because the origin is 0. So I think I enter in through r equals 0. How I exit, right? All of these will continue until they eventually hit, and it looks like we hit this circle. There are some that, of course, right, if we can draw like kind of skimming, and those ones are kind of both, 1 foot in, 1 foot out all throughout, but they don't really enter or exit so much. So again, I'm really just looking at the ones that are truly inside of our region. And for those ones, we always seem to exit through this circle. Now, I need an r equals, right? This is supposed to be an r bound. My circle equation, as we found, was x squared plus y squared equals 2. So I can use that, and I know in polar, x squared plus y squared should be equal to r squared. And this will enable me to solve that the radius of that outer circle there is √2. I mean, we already even said that at one point. So I'm going to exit through √2. Now, if I wanted to integrate across the entire circle, it's maybe not surprising that I would do a theta of between 0 and 2 pi, right? All the way around. Now, in my case, right, we don't want the entire circle. We only want a piece. And so this piece here, right, you could probably guess, given our picture is not half bad, that this is going to be from pi over 4 to pi over 2. So from 45 degrees up to 90 degrees. And you would be absolutely correct, right? And so a good picture is nice for this sort of thing. But you may wonder, right, how can I get this algebraically? Where does this hidden in the equations, right, that I could actually achieve knowing that this is exactly pi over 4 and exactly pi over 2? Well, so we can look at, we seem to know pi over 4 because this is where it skims this line y equals x, right? So this y equals x is actually something about our theta bounds here. So if I was to go ahead and pull off to the side really quick and think a little bit about y equals x and put this into our polar coordinate system. So, right, r sine of theta, r cosine of theta. Well, so long as r is not exclusively 0, you can cancel out an r on both sides. And then what I'm left with is sine equals cosine. Now, some people at this point may say, I know a place where sine is equal to cosine, right? If you plug in pi over 4, both of them are √2 over 2. So sine is equal to cosine. On the other hand, other folks may say, well, I want to be a little bit more careful and, instead of using the unit circle here, maybe use the calculator, in which case you could get just one theta by dividing by cosine on both sides. So if you divide sine by cosine, you get tangent. And if you divide cosine by cosine, you get 1. Then you could apply a tangent inverse. And again, assuming your TI-30 is set to radians, right, it will tell you that tangent inverse of 1 is pi over 4. And so here's two different ways that you can get that pi over 4 is how you are entering in. You are exiting kind of your upper bound for theta, right, comes from this line right here. This is a part of x equals 0, right, this y-axis, where you haven't moved to the left any, you haven't moved to the right any, your x value has stayed at 0. So likewise, if you wanted to know about your upper bound, you could start off with x equals 0, convert this into polar. So long as r is not exclusively 0, right, you can divide by that. And then the question is, when is cosine equal to 0? And the answer to that is, well, exactly at pi over 2. Still, the picture is very useful because that eliminates, for instance, like 3 pi over 2. So I'm not saying that with this method here, you can completely get rid of the pictures, but this is how kind of the algebra, the equations are related with kind of our intuition that we got from the picture. All right, so now we have the setup. And the last thing, right, it says to convert into polar integrals and evaluate. So we want to go ahead and evaluate this. So the first thing I'm going to go ahead and do is that I do see that both of these here have an r. So I'm going to go ahead and factor out this extra r. That means I'm going to have an r squared in total. And what I'm going to do with this, right, is that we know that so long as you have constant bounds and you have a function of just r's times a function of just thetas, that you can go ahead and break up your integral. Previously, we had done this with x's and y's. When I integrate my r, 1/3 r cubed. When I integrate my cosine, I'm going to get sine. When I integrate 2 sine, I'm going to get -2 cosine. And now it's just a matter of inputting in my values here. So this is going to be 1/3 and √2 times √2 times √2. You can write this as √8 if you'd like, or you can write it as √2 cubed, right? Either one of these is perfectly fine. When I plug in pi over 2, well, I'm going to have sine of pi over 2 is 1, and cosine of pi over 2 is 0. And then I need to subtract away when I plug in pi over 4. Sine of pi over 4 is √2 over 2. And cosine of pi over 4 is also √2 over 2. So a little bit of cancellation here. And so we're going to get 1/3 √8. Oops. 1, and then let's see, this is going to be inside there, that's -√2 over 2 after we simplify, minus a negative, so it'll be plus √2 over 2. Just a couple little simplifications there. And so this right here would be our final answer. So again, the main things, and I'll take a question here really quick, but I would recommend transforming your function first, transforming your dy dx, and don't forget your Jacobian, right? All of this is worth some partial credit. The bounds take the longest, right? And so, and require a picture and all that sort of stuff. And so those ones I kind of save for last. And then hopefully at the end here, the evaluation is not too bad. So that's kind of the order of operations I would take. Yes. Oh, so I didn't get rid of it. So I factored out an r from this x plus 2y's business. And so there was, once I factored out, oops, I don't want my highlighter here. Once I factored out an R, I apologize for skipping this step, and I appreciate you calling me out on it. But yeah, once I factor out this R, right, there's an R there, and then there's that extra R. So that's where the R squared came from. So it was accounted for, but yeah, I did skip that step, so I apologize it wasn't clear. Good. Any other questions on this one? All right. So then, let's go ahead and try another one. Find the average height of a single cone, or a half cone if you'd like, above the disk x squared plus y squared is less than or equal to a squared in the xy plane. So let's go ahead and maybe try to visualize this one really quick. So these are the positive z values for our classic cone equation. So maybe I draw my x, y, z coordinate axes here. We have our cone, our full cone would have negative z values as well. So this is only the positive square root. So we have a cone that looks like this. And of course, this cone would normally go on forever, except for that we're told that we're only interested in the piece of the cone that lies inside of this disk. And this disk, I mean, it'd be a little bit nicer. And you know, if I saw this on a homework question or something like that, I may get a running start by just first doing x squared plus y squared is less than or equal to like 9 or something like that first, right? And then I could do this variable a. But so this disk that we're talking about here is a disk in the xy plane. And this disk has a radius of a, right? Because at the full equals, it's x squared plus y squared equals a squared. So our radius is some value a. So again, normally this cone would keep on getting bigger and bigger and go on forever sort of deal. But in our case, our problem has specified that we only care about it inside of this disk of radius a. And of course, these should kind of line up very nice, because after that, it would kind of break out of that disk. So really quick, thinking about what are reasonable answers here for finding an average height. Well, at this outer bound of my disk, when x squared plus y squared is equal to a squared, notice that seems to be where the cone has its maximum height. So if I plug that into my equation of my cone, maybe instead of x squared plus y squared, I can substitute in a squared. So all the way up here, this has a height of a. So the cone is taking on different values for heights, right? The height near the middle or at the origin here is 0. All the way out to at the rim of the cone, we have a height of a. And so if I was naively guessing what is the average height, I would say maybe a over 2, half of it, right? Because it goes from 0 all the way up to a, maybe a over 2 or 1/2 of a, right? That's a reasonable average height. But on the other hand, it looks like there are maybe more points on the top half of the cone, right? Maybe because again, we're taking an average of the heights. Maybe because there are more points near the top of the cone, maybe it's actually more than 1/2 of an a. So this is, again, just kind of understanding when we get an answer out, what's reasonable or not. So I would say maybe it's even more than 1/2 of an a, but it's hard to say. Okay, so now let's get into our calculus. How do we solve this? Well, we are looking for an average value of a function. So remember back in, I think it was 15.2, it might have been 15.1, we came up with an equation for an average value of a function, and it went like this. We had 1 divided by the area of the region times the double integral over that region of whatever function we're interested in the average of, dA. So in this case, we're interested in height. What is the average height? Well, the height's usually given by the z values, right? So really what I'm interested in here is if I was to integrate z, what is the average height? Well, it's z values of what? It's the average height of the cone. And so we see that we have an equation for our cone where it's z equals the square root of x squared plus y squared. So this is going to be the square root of x squared plus y squared. And this is quite nice because right when we integrate, we don't often have z's at this point. We will when we have triple integrals, but with double integrals, we usually have just x's and y's. So okay, that's good. The next thing is that we need to look at our region. So the region that we're integrating over, where our surface is hovering above, is this disk, right, in the xy plane. This is a circle of radius a. And so we can get two things from that. First of all, we can get the area of that quite nicely. The area that's trapped within that disk is going to be pi r squared. In this case, right, the disk has a radius of a. So the area of this region is going to be pi a squared. And now the last thing is that we need to make a decision. Nowhere in this problem, and I'm imagining that I'm on the exam or on the final or something like this, nowhere in this problem does it say convert into polar. Of course, we're in a class that's all about polar, and so it's maybe not surprising that yes, we're thinking largely about converting into polar. But this problem doesn't say that, and so we need to think about what are the main keys, right, to know that we should maybe convert into polar. And so, because as of right now, we have three different options. We could integrate with respect to y first, then x. We could integrate with respect to x first, then y, or we can convert into polar. These are our three options that we have. And so largely, the main thing here is that our region is a circle. This is going to be and if we look at it kind of straight on, which is not a bad idea either, right? So this is, if we were looking at it kind of from above, our circle of radius a that our surface is hovering above. This is our region. And so anytime you have a region that is a circle or a part of a circle, right, I would be leaning or thinking heavily towards polar. The other thing that's kind of nice in this case is, right, if we look at our function, the square root of x squared plus y squared, right, this is very nice that we can convert this into polar, right? We know that x squared plus y squared is equal to r squared. So these are all things that kind of are leaning me towards that polar would be a reasonable way to do this. If I don't use polar, right, I'm going to have to enter in through maybe the bottom half of the circle and then exit through the top, right? I'm going to have square roots of things, and I could be incurring some trigonometric substitution. And so that's kind of why I would stay away from, when you have circles, these other two. Not to say that they're never right, but I wouldn't go there first. So if I'm setting this up in polar, this is what I would write next. Swap out, instead of x squared plus y squared, for my polar, in this case r squared. Make sure that when you convert into polar, you include the Jacobian, this extra r factor. At this point, we already have our picture as well of our region, and so I could even quickly set up my bounds. So my bounds for r in this case are going to be from 0 to a, and my theta, because I want the entire circle in this case, is going to be from 0 to 2 pi. There are no restrictions on theta. So again, you can kind of think about quite literally, if I was traveling in my r direction, how do I enter and how do I exit? Right, and I would enter in through r equals 0. As soon as I take the tiniest step off of the origin, I am in my region. And I exit through x squared plus y squared is equal to a squared, right? That outer circle there, how I exit, is of course equivalent to r equals a. It's a circle of radius a, right? That r literally stands for radius. All right, so now we have the setup. At this point, the evaluation usually comes pretty fast. So I've been, separating my double integrals whenever possible. Of course, you can do that in this one as well, but I'm going to go ahead and get practice using the other way as well. And so let's go ahead and just take this one at a time here. So if I was to integrate r, well, let's maybe first simplify this, right? The square root of r squared is going to be r times another r, so that's going to be r squared there, right? So if I integrate that, I'm going to get 1/3 r cubed, and I need to evaluate that from 0 to a. So this is going to be 1/pi a squared. And then I'm going to have 1/3 a cubed. This is all constant with respect to theta. So when I integrate with respect to theta here, let's go ahead and maybe pull this out, 1/3 a cubed. And this is really just like the integral of 1. So when I integrate a constant with respect to theta, right, we just get that theta. And then we need to evaluate that from 0 to 2 pi. So my final answer here is going to be, let's see, we can already start doing a little bit of the canceling. I'm going to have what? A divided by 3 pi times 2 pi. So there's going to be a pi that cancels on top and on bottom. And it looks like my final answer is going to be 2/3 of whatever a is. So again, naively, I guess that maybe the average height of points on the cone were going to be about 1/2 of an a, because again, kind of near the middle, it was height 0, and near the edges, it's height a. But we did think that maybe there are more points near the top than there are near the bottom. And so you can actually see that on average, if you consider all of the points, right, that there are actually more points on the top than there are on the bottom, and it makes a difference. So the average height actually, if you consider all of the points on the cone, has a height of 2/3 a. Questions on this one? Yeah. Where did oh, so this isn't denominator, sorry. This is me just rewriting this. So this, maybe it'd be better if I put above and with like some curly brace or something. There. So when you simplify the square root of r squared, you get r times another r, combined makes r squared. Good. Any other questions? All right. Well, one last question, and then we will talk a little bit about 15.5 stuff today. It's just a quick application, just as you saw, 1 page of notes. So we'll do that really fast. So find the volume of the solid bounded between the plane z equals 0 and the paraboloid z equals 1 minus x squared minus y squared. So again, of course, being in a section here that's all about polar integrals, right? We're thinking that we're probably going to have to solve this with a polar integration. But I do want to, again, put us in the mindset of, being on the final exam, for instance, because this problem here doesn't say anything about a double integral. And so it uses one of these key phrases, right? Find the volume. And so we need to remember that double integrals were used in order to find a volume between some interesting surface and the xy plane, aka z equals 0. So in this case, these words mean that I'm going to be doing a double integral of 1 minus x squared minus y squared dA on some region. So we're interested in the solid bounded by the plane z equals 0 and this paraboloid. So if I was to go ahead and take a minute and sketch these, of course, z equals 0 is just the xy plane. Don't really even need to shade that bit in so much. And then this paraboloid, well, we got lots of practice sketching paraboloids maybe back in 12.6 when we first saw quadratic functions. So if I saw this one here, and maybe as you do more of these, you don't need to do this out in all the full detail here. But if I was to think really quick, if x equals 0, what does that cross section look like? right? So I might have z equals 1 minus y squared. So this is going to be a parabola that's opening in the negative z direction here in our yz plane, right? So we have y's and z's in my equation now. It starts off at a z value of 1 when y equals 0. And when y gets bigger, right, it kind of goes downwards because we're subtracting away y squared. Likewise, if I was to do y equals 0, I would have z equals 1 minus x squared. So now in my xz plane, kind of a very similar story, but now I'm trying to draw this again with my x's and my z's. So something like this. And we may even do when z equals 0. Of course, this is when it intersects, right, this xy plane. Z equals 0 is also kind of one of these equations given to us. In which case we get 0 is equal to 1 minus x squared minus y squared, which is equivalent to a circle of radius 1 in the xy plane. So this is intersecting here at a circle of radius 1 in our xy plane. So the region that's bounded by these two surfaces is this stuff right here. Really, the most important thing and what we're trying to gauge from this is what does our region that we're integrating over look like, right? What is that R in my little subscript there for my double integral? What am I integrating over? And now we can see that this surface, right, what I've shaded here, is kind of hovering over this circle in the xy plane. And if I was to pick this up and look at it directly on, in the xy plane, we found out that this wasn't just any old circle, right? This was a circle of radius 1. X squared plus y squared equals 1, right? So if I was to, again, shade this in just the xy plane looking at head on, this is a circle of radius 1. So now at this point, again, I'm imagining I'm on the final exam. I have to decide, do I want to integrate this with respect to y first, with respect to x first, or use polar? And the main things that emphasize polar is, right, our region of integration is a circle, or part of a circle. Moreover, we also see something very nice up here, x squared, plus y squared once you factor out that negative. And so those two things really combined means that I'm leaning hard towards a polar. So this is going to be 1 minus, and then this would be x squared plus y squared, if you factor out that negative. So x squared plus y squared, of course, we can transform into r squared very nicely. And when I switch from dA into polar, again, r dr d theta. A mistake that I see every once in a while, and if you type this in exactly as I have it here into WebWork, you would get some points wrong, right? This would say that it's wrong. Because this r needs to be multiplied by the entire function here, right? So it's not just that second piece, but it's dA, right, which is being multiplied by the entire function there. And so you need to include some parentheses, or you can distribute immediately. All right, this one's pretty nice. What are our bounds for r? Please. 0 to 1, yeah. So again, with our region here, thinking about as I move in my r direction, how do I enter and how do I exit? Well, as soon as I take the tiniest step off of the r origin, r equals 0, I'm in the region, and I exit through r equals 1. Because I have the entire circle here, we're going to be integrating thetas from 0 to 2 pi. This one I'm going to showcase maybe the fastest method. If you were doing this on a quiz or an exam, what's the fastest you could do this without getting points marked off? And so you can separate these two, right? We have nice constant bounds. we have just r's and just thetas, right? Really our theta function here could be just 1. And so if I integrate 1 with respect to theta, I'm going to get theta. I need to evaluate that from 0 to 2 pi. And when I integrate when I integrate r, let's see, distributing this, integrating r here, I'm going to have r squared over 2. And integrating r cubed, I'm going to have r to the 4th over 4. So if you can get to this point where you're comfortable with showing this amount of work, that's kind of the minimum number of steps that I expect to see on a quiz or an exam to get full credit. Nope, bad simplifying. So 1/2 minus 1/4 is 1/4. 1/4 times 2 pi is going to be pi over 2. So the volume that's trapped between my paraboloid and the xy plane is a volume of pi over 2. All right, any questions on this one? All right, well, one more page to go then. If you read in the textbook, 15.5 has a lot of applications. This is where they start. I mean, you can learn about moments of inertia and all this sort of stuff here. And so if you're taking a physics class and you want to see how calculus 3 relates to that, there are more topics. However, in our class, really the main thing that we want to be able to get is mass from density. And that's going to be our main application here. So if we have some density function, which is going to be given by sigma that relies on x's and y's. And this is of a thin sheet of something or other. So lamina, the same root word as laminate. So laminate flooring and stuff like that. So, okay, thin sheet. The mass of the lamina can be given then by the double integral over our region of the density dA. So we have already seen mass from density once before. This is when we had like springs and stuff like this. So in 16.2, we saw some mass from density. So as kind of a side note, if you had mass from density in 16.2, this is one of the applications of line integrals with scalar functions. So back then, I think I don't think it had a name, so maybe just FDS, we'll say. So if you have like a one-dimensional spring, right, which maybe has a length to it, then you can calculate its mass by doing a line integral of our density function to get the total mass. So if you add up basically the mass at every single point, you're going to get the total mass. So in this case, we don't have a spring, but we have a two-dimensional object, right? A thin sheet of laminate. And then if you add up over however much region this laminate is over, right, that's going to give you the total mass. So this is actually our second instance of mass from density. So here's my example that I wanted to talk about. A lamina has a density of x squared plus y squared over the region R shown below. So this is a nice square. It looks like it has a width and a height of 2, right? Ranging from -1 to 1 in each case. Calculate the mass. So again, imagining that I'm on the exam or the final or something like this, notice this does not say do a double integral. It uses some code phrase instead, right? So we need to remember that one of the things that double integrals are good for, one of their applications, is to find a mass from a density. And so if I do a double integral of x squared plus y squared, my density function in this case, that this right here is going to give me my total mass. Now, again, we're coming from 15.4, where we've been doing lots of integrals in polar. I have a function, x squared plus y squared, which would look beautiful in polar. R squared, done, right? On the other hand, my region is a square. It looks quite beautiful in Cartesian, right? I know that I would enter in through y equals -1 and exit through y equals +1. X's would range from -1 to 1 as well, right? That this is not circular at all. And so what I wanted to emphasize here in my final remark, and of course we'll solve the problem as well, but so right after leaving section 4, you'll have to decide whether to integrate with respect to Cartesian or polar coordinates. A good rule of thumb is the region determines this, instead of the function. So I would put always more weight on the region than the function. So if you have conflicting information like this, where the function would look very good in polar, and yet the region looks very good in Cartesian, go with the region. My claim is to set this up in Cartesian, it's very fast, right? Y's go from -1 to 1, x's go from -1 to 1. There, we've set it up. If, on the other hand, you decided I want to do this in polar, I'm just doing polar stuff, the function looks good in polar, think about, as we travel in our R direction, how do you enter and how do you leave your region? Well, we always enter in through R equals 0. That part's nice. However, depending on what your theta is, sometimes you're leaving through this top R curve up here, right? So if your theta maybe ranged from pi/4 to 3pi/4, this is how you would have to exit, which this is part of y equals 1, which would be r sine theta equals 1, which is if you wanted to solve for r equals being an r bound after all, you would have to have r equals cosecant of theta. That would be from pi/4 to 3pi/4. Next up, on the next region, right, you'd be exiting through the left-hand side. That's part of x equals -1, right? And that has it, so you'd have to have 4 different integrals in order to evaluate this out in polar. By comparison, I'm done setting it up in Cartesian. So that's what I mean, that the region is more important than the function. Really, it should be the region that really determines whether you integrate in polar or not. So with our few minutes left, let's go ahead and evaluate this. There's no way that we can split this up using our trick because we can't separate this as a function of x's times a function of y's. And so we do need to evaluate this one by one. When I integrate with respect to y, I'm going to get x squared y plus 1/3 y cubed. When I plug in 1 for y, minus when I plug in -1 for y, and notice that I took care of all of my x squared stuffs first here. Let's do now the y cubed. Plugging in 1, I'm going to have 1 cubed is 1. Subtract away, -1 cubed would be -1. So this is nice for just combining like terms' sake. Now I need to integrate with respect to x. When I integrate, let's see, that's 2x squared. So that's going to be 2/3 x cubed. And when I integrate my second one, well, that's 2/3. When I integrate that with respect to x, I'm going to get 2/3 x. And again, I need to evaluate that from -1 to 1. So again, let's take care of the x cubed stuff first. When I plug in 1 for x cubed, cube that, I get 1. I subtract away, when I plug in -1 for x cubed, I'm going to get -1. So minus a negative will be plus. And then for my 2/3 x, if I plug in 1 first, and then I subtract away when I plug in -1. And so it looks like I'm getting, what, 4/3 plus 4/3. That'll give me a total of 8/3 will be the mass. All right, so yes, Again, the emphasis here, why I wanted to bring this up, is that the region is more important than the function when determining if you want to integrate with respect to polar or not. All right, well, that's the end of the class. Any questions? Yeah, in the middle here. Yeah. There you go. All right, well, I'll stop the recording here, and if you do have any one-on-one questions, I'll stick around for those. Otherwise, I wish you have the